Hello, Professor.
Can you stay a moment after class? Okay, great. Okay, stuff that I want you to know that you need for homework 2 is be playing with the perspective wrap or perspective distortion matrix. I think that I'll get to it today. The buffer algorithm. What homework 2 will be on homework 3 will be on triangulated mesh. With Billboard or without Billboard, I'm not sure, but will be on WebGL, so you might want to start doing it. So why WebGL and why fragment programming, I hope to get to today. Because that would be the explanation of why we are going to some of the gymnastics that we are going via. And I'm missing. That's a wrong one. Yes. It was a wrong one. Yeah, and for the lecture tomorrow, I don't know much more than what I send you on the piazza. She is a faculty candidate. The topic sounds relevant for us and interesting for us. So tomorrow at 11 at room 223, the big room, down there. Yeah, and we're missing some cameras, but okay, so any question about homework 2? Cool. So we talked about BSP, where I was completely hand-wave about how exactly. Yes, sir.
Okay, this is going to sound really bad. Can you read a JavaScript file directly as a JSON object?
I don't know.
Because
Can I read a JavaScript as JSON? What?
Because because we're supposed to parse a JSON file, but we're given a .js file instead of a .json file, so that's why I was confused.
Just parse it as a JSON, it works.
Okay, thank you. Yeah.
Or JS.
That's the problem. I don't know how to parse it as a JS file. But
No,
It's the exact
no.
same.
You just use the from JSON.
It's supposed to be in your. Once you read the file, you can ask what is you'll have one array of spheres, each one with its attributes, and one array of billboard. Each one that will ask for which image file you want to have. And
that was the file format. That was all. I think I got it now. Thank you.
okay. Yeah. You'll have another type of files of mesh, of triangulated mesh files also that will play, and none of them are supposed to be read by humans. Okay, so basically we talked about the painter algorithm. Said we have some line L, and out of this L there is a set of triangles T1, T2 until T17, another set of triangles T18, T19, T20, one on one side of L, one on the second side. I'll build a tree where L will be at the root, and I'll decide that everything above the line will be, say, on the left, so I'll call this set S1, I'll call this set S2, and I recursively build my tree on the set S1 because it's one side of L, S2 because it's on the other side of L. Think that if I have triangles that are just on L, remember L is a plane, the 2D is just for visualization. If I have a triangle that is exactly on L, I can actually avoid storing L and just store what is a segment. If I really want to save every bit, then I can actually store the triangle itself at the root instead of storing the object. For simplicity, let's just say that we are storing L and I don't have an object that is fully inside it. What I can have are triangles that are on both sides of L, and they will be needed to be treated separately. For example, T23 will needs to appear both on the left side as well as on the right side, and maybe during the visualization, during the depth order, I'll do something about it. Algorithms for building. So that was the first level of the tree, and from now on, I'm just continuing recursively. So when I build the subtree for S1, I completely ignored S2, and vice versa. Opposite. So that's why the lines that partition one subset, as far as I'm concerned, just to show them, this line stops once it hits a upper hierarchy of the line, right? So there is a hierarchy between the lines, and when two lines meet each other, one of them, the one with the lower hierarchy, the one that is lower in the tree, will stop. Doesn't have the line L2 doesn't have any impact and will never be used on the opposite side of L0. And why? Because L0 is higher in the tree. So that's about BSP. And we talked about BSP in this context because we talked about the painter algorithm. But we said if I have a viewer V on this side of L, the viewer first check at which side of L am I. And once I know at which side, that is, in this case, V is somewhere in the side of S1, then when I render the object via the painter algorithm, first render the one in the opposite subtree, and then move and paint the one on S1. Why? Because painter algorithm says I'll start from the furthest away object, and the last object that I render is the one that is closest to me. And as we mentioned, it's a bit counterintuitive, and it's a bit against level of details that somehow I'd like to maybe, like it's intuitively, if something is very close to me, then it takes more of my image, so it has higher importance. That's completely the opposite here. I'll start rendering from the very last object, very last triangle, even that's the furthest away for me, and even if at the end of the day I don't say anything from it. Later in the course, I'll show you I'll dedicate half an hour to try to put a few tricks together, including that try to address exactly very large scenes. We see that BSP works nicely with GPUs, and with GPUs we have a few tricks that help me for a sub portion of the tree. Do I need to render any of it at all or not? And we'll see a very cute trick to see if visiting a portion of the subtree, let's say, here is a portion of the subtree that contains the elements that's transparent green. Here are only the triangles from T1 till T17. They are inside S1, but inside S1, let me highlight it, and that's just a promo. Inside S1, here is T1 T17, this small subtree. I want to know whether I should bother render, and to make it practical, 17 triangles is way too small. Make it when it's 17,000 triangles, but they are nicely concentrated in the same area of the BSP. In the rendering process, you want to ask, should I paint any of it? Should I spend time on any of them or not? What we'll do in the first pass is place all of them in one green box. Use the GPU, and the viewer will need to decide, do I see any green pixel? It's very unique green that doesn't appear in the image. Inside the image as a viewer, do I see any green pixel? And if I don't see any green pixel when the viewer is right here, then I shouldn't expand the subtree. And that's a very practical trick. GPU, as we'll see, works very well. Place bounding box around sub-region of the tree, and that's how you actually use it properly. And as a first pass, instead of having all these many triangles, you'll just have one big box, literally a box. Axis parallel box takes what the minimum x, minimum y, maximum y. Place this box out there, and then ask for the viewer, do I see any of them or not? So GPU with BSP with the trick of replacing, treating differently far away object and very nearby object will work very well. And at the same time, if I'll tell you that you do see all of them, but my viewer going to stay for a long time, the viewer, the player, is going to move a bit, but only in these regions. Very limited in its movement. I already told you, you see at least one of these sweet points. So you see some portion of this subset of triangles T1 till T17. And you want it dynamic. That is, the viewer might move, but only a bit. How would you handle these guys?
Change the bounding box based on the angle of the viewer.
The use of the bounding box, I mean, it's hard to understand even without the accent, but the use of the bounding box is that I replace a big volume by a bounding box, put their triangles, and then as a first pass, I ask, do I see any of the green pixel? Because if I don't see, if other triangles occlude all the green pixel of the bounding box, then there is no reason for the viewer to worry about these triangles at all. So it's a filtering trick. And you can do it for a few bounding boxes over here. My question now is, if I passed the first pass, the first test, the viewer does see some pixels of the green, maybe a lot of them. But I'll have plenty of frame, thinking about it as a video game, I have plenty of frame or videos that I generate where the viewer moves very little with respect to the triangles over here. Yep. You have again, it's not 17 triangle, it's 17,000, 17 million. And the importance of that the viewer moves very little is that triangles that are near the user should be treated differently than triangles that are far away comparing to not a single point, but comparing to the whole movement.
Perspective, is that what you're getting at?
Is it maybe that we only have to like do that check on those further away objects once we've moved closer?
So you look at them and you project them and replace all of them with create a billboard for what the viewer sees for these triangles, because it doesn't change, at least not significantly, when I move. So it's a very complicated scene, but if it's on one hand, I'll use the GPU to decide whether I see it at all, and on the other hand, if it's very complicated, but it's far enough and I'm not running into the troubles that we will discuss more with billboard, with imposers, I can think about the whole thing as one 2D image that I just put on a billboard right here. Because as the viewer moves, this part of the image is not changing. The viewer, that is, when will you give up, changes. That some parts reveal itself or does not reveal, or one thing occludes itself, depending on where I am in the view. If it's far away and I'm not running into these issues, for example, all these objects are far away in infinity, it just asks to be replaced by a billboard, then the extreme case of billboard are what you know as environmental map, what you put as the infinite world above, below, around you. We'll talk about all of it in texture. Okay, so that's about the painter algorithm and BSP. Once again, given the viewer, you're visiting first the subtree that does not contain the viewer, and at which order do you, when there's a triangle like the subtree that does not contain the user, you continue recursively. the subtree is full of its own half planes, etc. Now, we will have the whole chapter about accelerating data structures, like quadtrees, like hash function, geometric hash function, all helps us do a lot of things much faster. BSP by itself I'll spend less energy about. I'll just mention one algorithm that works very well in practice. How would I build my BSP? I'll pick one of the triangles. T17, T18, and I'll create a plane that contains T18, and that would be the line that I'll pick. So that would be L. What's so special about T18? Well, there are better algorithms, but if you don't want to waste much time, pick one of your triangles at random. And as you might get a feeling from randomized algorithms or from knowing enough about sampling from basically any data set. If you pick one at random, you have a good chance that it doesn't split. You don't have a lot of triangles that goes from one side to another side, and you'll have good ratio between the left and the right. And we leave the construction of the BSP at this point. So again, at each iteration, just pick at random one of them. That's an algorithm. Of course, there are better ones depending on trade-off between construction time versus the qualities that you're getting from the BSP. We discussed it in much further details in the two-dimensional case. And in the two-dimensional case, the beauty is that you can prove that you'll have only n log n many pieces with high probability. Again, I start with n triangles. Where do I get more than linear number of pieces? Because I have triangles that is stored twice. I need to split it according to the plane. I need to split it maybe multiple times, but multiple is not ridiculously multiple. It's only log n with high probability. Moving along. We talked about creating the BSP. Let's talk about the Z-buffer algorithm. That will have a different approach for the whole thing. So if I think about really do the hidden surface removal by, here is one rectangle, here is one triangle, and I need to compute from the viewer points where is this edge, and now split this triangle into one quads. Calculate where are the vertices of the quad that is visible to you and which parts are not visible. That takes a lot of time, a lot of calculation, and in most cases unneeded. You don't want to ask what is visible to the user exactly. I limit my, I have to go out through this hidden surface analysis if I assume that my image has infinite resolution, infinitely many pixels. But it's not the case. The case is that I only have some number of pixels, say 1,000 by 1,000, and I only care that each one of these pixels only will show the color of the nearest triangle to it, if I assume no transparency. Okay, so I'll just check for, I can do ray tracing, as you did in homework 2, just for the pixels themselves. You actually solved hidden surface removal because you gave, between the billboard and the spheres, because you just gave the correct answer for every ray, what is the minimum time, given that this ray hits a set of objects, what is the first object that it hits. So you already solved one hidden surface removal. And we'll try to go along with this approach of only these pixels are anywhere. So I'm not generating an image that has infinite resolution. It only cares to be correct in terms of depth. Depth, remember, depth, is this before this or is this after this? Only at the pixels that you are checking. Okay, so what's the difference between ray tracing versus the Z-buffer algorithm? In the ray tracing, the loop is you're generating one pixel, Pij, factory of a pixel, Pij, and now you have the recursive ray tracer code that takes this one pixel, this pixel generated one way, and now I have a loop that runs towards the object. That is per pixel, one towards the object. That in ray tracing. And of course, once you find where this ray hits, maybe you want to recurse it to see shading effect and shadow effect. Z-buffer algorithm says the opposite. It will be presented when these objects are triangles. It's neither when it's triangles, or it used to be popular to work with quads as well. Quads went out of fashion. Today it will be triangles only. And for each such triangle, if T is relevant to the image at all, we already saw some tricks that tell us that some triangles are not relevant, for example, by doing the backface scaling. Remember, look at the normal points toward me or not. Maybe this triangle is completely outside my view forestone. But if it is relevant for something, then project it on the image plane. And for every pixel Pij that is affected by this triangle, here is what is interesting. Check if, because of this new triangle T, I need to change the color of Pij. Remember, what did the painter algorithm tells us? Painter algorithm said I'll print, here is one blue region, here is one red triangle, but if I'll first render the red, if the red is further away than you, and then every such pixel inside, that's in the painter algorithm, if blue is closer to you, I'll change the color of every such pixels to blue. So that will be a bit similar, the painter algorithm, and the Z-buffer, except that the decision making that I'm making are not trying to be global. I'm not necessarily trying to insert the triangle in a fast order. Like, I can play with good order so to make my algorithm faster, but the Z-buffer doesn't require any particular order of the triangle. It just says at every moment, for all the triangles that I had so far, from T1 up to 317, for all the triangles, every pixel Pi has its own color, given the triangle from T1 till T17. Now T18 is inserted, check which pixels are affected, and maybe, if it's relevant for them, change their colors to T18 based on a very simple check. So let's see the Z-buffer in a bit further algorithm, a bit further details. So Z-buffer requires you to keep two arrays, two-dimensional arrays. Each one with a resolution of the image. One will be the color buffer, Pij, that says every pixel needs to store its current color. The next one will be the depth buffer. And I remind you what we discussed last meeting. Depth of a point is what's the distance from the pixel in the image plane until this point. And we'll only talk about orthographic projection. All these ways are parallel. So the depth of a point is always this horizontal distance from the pixels up to this point. I don't really need to do ray tracing. So depth buffer stores the distance from the pixel Pij to the relevant point of the nearest triangle. So pixel 2, 1, pixel 2, pixel 3 over here stores 8.77. Why? Because the distance from these pixels going horizontally until it hits the blue triangle is 0.77. This pixel, pixel 8, stored 427 because that's the distance from the pixel till this point. So depth buffer stores these distances, and the color buffer stores the color of the triangle that is the closest to me. So this pixel says the triangle that is the closest to me is a blue one, so that's the color that I store, the blue pixel. And I assume right now that triangles are completely opaque. If I want to play with semi-transparency, then I'll need something that is built on top of the Z buffer, namely the A buffer and stencil buffer that can be a bit more subtle about the closest object, but maybe also the object right after it, and maybe the object right after it. So I'll have a fixed number of objects, but always most important is the closest one to me. That is, this pixel is blue because the nearest object along this way is blue, and so the color buffer stores blue, and the depth buffer stores this distance. Even though there is yet another triangle that this way hits. And now I'm inserting yet another triangle. I just inserted yet another triangle. And for every pixel in the image plane, ask what is the distance to this triangle. And actually I can be a bit smarter, only the pixels that are affected or that are relevant for this triangle needs to do this depth check. But that's the heart of the Z buffer algorithm. So I have a new triangle T, T4. Let's show you again, especially to admire myself that I put the animation so well to GeoGebra images. Almost perfect. T4 is just one more triangle that I inserted. Again, the order of insertion is irrelevant. And every pixel asks what is the distance to the relevant point of the new guy. That's the point Pij from the pixel until I hit the triangle. Of course, different pixels have different answers about what the distance to the new guy. But I'm not committing that the new guy has the same distance to all the pixels. It's not necessarily orthogonal to the image, to the rays. It's not parallel necessarily to the image plane. You see, these three pixels have different distances. We'll have to talk about how I compute these distances. And now, if the depth buffer of pixel 3, this guy, if the depth buffer is oops. The depth buffer of this point was 0.77. Why? Because 0.77 was the distance to the blue triangle, to T1. Now I'm inserting the red triangle, the distance to the red triangle, across this ray from this pixel is smaller than the 877 that I store over here. What should I do in this case? Then set the color of these pixels to be red. I don't have this animation, but the color of this pixel should have changed from blue to red, and the depth buffer, the distance to this triangle, should be updated because it's smaller than the optimum. What should I have done if the depth buffer is smaller than the distance? Let's say that I'm just re-entering T3. Well, the distance from P3 to T3 is larger than the distance to the nearest one, which was already T1, so I don't change its color. Then I do nothing. Make sense? I could have replaced it by the distance across the array, but I don't because that's how the hardware wants the input to be. And that's a Z-buffer algorithm, and it's efficient even if you run it sequentially, one per pixel. And it's of course more efficient if your GPU wants to run it for each pixel, for all the pixels at the same time, or for a lot of the pixels at the same time, which is what your GPU would like to have. And of course, and so I described it as a dynamic algorithm, even though the result is a static one. I described it as I'm inserting the triangle once by one. What does the Z-buffer algorithm doesn't want you to do? It doesn't want you to remove a triangle or to move a triangle, because if after having the nearest buffer to T1, I'll delete T1, well, I need to change the depth buffer to be this distance, but I don't have any good algorithm to do it. The only way that I know how to remove one triangle would be reinsert all your geometric scenes from scratch. Make sense? Insertion as much as you want. That's how the algorithm works. Deletion, try to avoid, or change the location of the triangle. Much less efficient. Okay, and that's algorithm classical. You had, at least for the last 20 years, I think for the last 30 years, you already have hardware that can support this thing in parallel. Now, the depth buffer I can also show as an image by itself. You have values of pixel, and every pixel just map into a grade level. So here is the image. What you see on top is a color buffer of a scene. What you see on top is a color buffer of a scene, and it's mapped so the closer a point to you, the smaller the depth, the darker the point is. So points that are very close to you are right here are much darker. Points that are at infinity are white, and different shading level, different darkness level tells you exactly what's the distance. So this image is exactly one by one the depth buffer. Okay, you can, it's a buffer, just make it, call it an image and present it. Right. This is not a fancy visualization of the depth buffer. This is a depth buffer, just called it an image. And as we'll see, we can have a lot of great algorithms that works by taking the depth buffer, let's say the depth buffer from the sun. I'll make one pass of all my geometric scene from when the sun is the one that look at the plane. Look at the image of what the sun sees, throw it away, I have no use to it. Look at the depth buffer from the sun, and now make a picture of the geometric scenes from the viewer point of view, but some objects are in the shadow. How do I know if it's in the shadow or not? Depending what its distance to the sun. If its distance to the sun is exactly what I think its distance to the sun is, across this way, then the sun sees it. If the distance in the relevant point is smaller, I'll have much more details about this algorithm, and maybe I'll let you implement it. That's how we used this image, thinking about it as a texture, relevant to the many application of texture algorithm in this course. We'll talk a lot about texture. One of them will be exactly take the Z buffer, the depth, Z buffer, depth buffer, same thing, the depth buffer, and use it to decide about shadows from various points. We'll revisit this topic when we'll talk about, talk about applications of texture. Any questions about the Z buffer algorithm?
What is that technique of doing shadows from the depth buffer? What's that called?
Chapter part for how to use Z buffer to create shadows. I believe that it's shadow maps, but it's you want to say here is the sun, and I have the depth from the sun to various objects, and the depth of the sun to, I have in the depth that the depth from the sun to object 1 to P1 is exactly this distance, so I can decide that P1 is illuminated, while at the same, sorry, that's my viewer. I look at the depth buffer after making one pass from the sun. Now I have the viewer, and the viewer sees a point P1, look at the correct pixel of the depth buffer, and realize that the P1 is that the sun, when it looks at this direction, reaches all the distance to P1, while for P2, if you think about the way that emerges from the sun to P2, it will say that's the distance to this object that I stored. It's D2, which is not the distance that I expect to see from the sun from this pixel, and that's how I decide that the point P2 is in the shadow. So very, very fast algorithm to create the shadow map by doing two passes of the Z buffer, one pass. When I'm saying a pass of the Z buffer algorithm, I mean do these things. When you iterate through all the triangles, of course according to where the V buffer, everything is according to your viewpoint. Do one pass of all the triangles first from the sun, take the shadow, the depth buffer, and use it to create shadows on another pass of all the triangles, but this time from the viewer point of view. Another example, fancier. Okay, depth, this time closer is whiter, and that is far away points are dark. Again, original image, and just look at the depth buffer and just express the value as a grayscale. Okay, once again, Z buffer. Once again, Z buffer algorithm for the scene. For every pixel XY, do put the maximum that you have such a constant maximum depth. For each polygon, each triangle Q, look at P and project it into the image plane. Project it into the image plane, so that's Q. And for each pixel XY, do Z equals to the depth of Q at the point XY. As we said, different points have different depths. different distance from the pixel. And if z is get from what I stored, get z at the same pixel, then change the depth at this point to be the minimum distance, and change the color at xy to be the color of this new object that you just inserted. And do it one per each triangle. Okay, so here is a final image plane, yet another example. Here is the, I inserted the first triangle, triangle 1. So my color buffer that store RGB. All the relevant pixels being assigned to red. And here is my gray level. Insert the green triangle, nothing interesting happens. Just this new triangle also in the depth buffer. At this point, you are inserting triangle 4. Then order is arbitrary, so the relevant pixels are larger. The relevant depth of triangle 4 is larger than what I already stored for as a result of triangle 2. But the pixel doesn't care where this depth came from. Pixel just said, I know what is the distance to triangle 2. Now you are inserting triangle 4, but the relevant pixel is larger, the relevant depth is larger than what I already had, and that's why this pixel remains green despite having the blue triangle. So it's like the painter algorithm, but just in the pixel level, not in the trying to sort all the objects, just each pixel by itself. Only update itself when it sees something closer to it. It's like you're creating the image, but your image consists of only one single pixel. Okay, and finally, triangle 3. Here is its depth. It's closer than triangle 4, and that's why I changed the color of these pixels from blue to orange, because it's closer to me. But how do I know the distance to a triangle? I'll need to know the distance for each triangle. The triangle are given to you by the 3 vertices. I'm not going to make it now. It's a triangle. I gave you the 3 vertices, and you have some point in the interior of the triangle. And I want you to compute the depth, the distance at this particular point. And for this, we are using barycentric coordinates. Extremely useful term, because the way we are going to compute it is we will compute weights, the weight with respect to a point, with respect to every vertex. And once we have these weights, we are going to use the weights for many other applications. We'll store the weights, and why WebGL? For many other reasons, because it will compute the weights for you automatically without you needing to worry, as well as applying these weights in a linear interpolation for any properties that you ask WebGL to do. So in particular, it will calculate the weights and the distances and interpolation of colors and interpolation of normals, all seemingly without you needing to ask it for each point individually. So let's talk about barycentric coordinates. When my input is just a pair of points, A and B, what will be the barycentric coordinate of a point P somewhere along this triangle? I want to give a weight W, it should be capital A here, sorry, the weight of a vertex A and the weight of a vertex B. Given the point P, I want to give each vertex a weight somehow represent the vicinity of P to each one of the vertices. And I'm doing it in a bit counterintuitive reasons, and the reason that I do it in such a strange way is that it will make the explanation about the 3D case more digestible. So stay with me despite that you all know how to do it. So I want to give a weight to the vertex A. How much should it affect P? and similarly for B. So what do I want these weights to be? It's numbers, W1, W2, WA, WB in this case. Maybe it's triangles, so there is 3 weights. And I want these weights to be a convex combination. When do I say that weights are convex combination? It's a very clear definition. Weights are a convex combination if each WI is non-negative, that is larger or equal than 0, and they sum up to 1. That is, WA plus WB should be 1 if there is only 2 of them, and in general, if I have more than 2, then the sigma WI should be 1. Sigma WI should be 1, then I'll say that they are convex combination. And I have a point P here, and I want to ask, what is the contribution of the vertex A? What's the contribution to the vertex B? That's it. Weight of A and the weight of B. Answer. Look at the segment from A to B, and look at the sub-segment. I want to compute what is WA. Look at the sub-segment, but there are 2 sub-segments here. Meditate on the one that doesn't have A on it. Meditate on the one that doesn't have A. Look at the length of the segment. Apologize. Should have noted. So WA, ignore what written, is the length of the segment from P to B. From P to B, that is a subsegment that doesn't have A, divided by the length of the whole segment A minus B. I want to say that this is a contribution of A. And similarly, W of B should be what of the 2 segments don't have A. It is the length of the subsegment from P minus A divided by the length of the whole segment, A minus B. So just switch these 2 terms. And now I have these 2 weights. Are they convex combination? If P is between A and B, then yes, they each positive, because this is shorter than this. And what does it tells me? It's the sum of both of them is exactly 1, because it's this divided by the whole thing, and this divided by the whole thing. What happened to P as I'm moving P closer to A? As I'm moving P closer to A, then I expect the color of P to become reddish and reddish. You have more red and less blue, which is exactly what happens, because now as P moves toward A, then the length of this guy is almost the whole length of the whole thing. It could get closer to 1. And on the same time, the contribution of B, W of B, look at the whiteboard. Oh, over here, the contribution of B should be smaller and smaller, but as P moves toward A. And exactly the opposite will happen if P moves toward B. Then the portion from A to P, that is W of B, will be closer to 1, and the contribution of A will be smaller. And using this formula, it's great, because now you can do linear interpolation, and it will give you for every point on the segment. If I take these 2 weights and apply them by the location of this endpoint and the location of this point, then as I'm changing the 2 weights, I'll generate all the points between them. That's if the attributes that I assign to the vertices are their location, x, y, z. I can also use the very same weight, but now it's colors that I assign to each one. And now I get a linear combination of the two colors. I interpolate between the colors. I can add other attributes as well, like direction of normals, and it will interpolate between them as well. So it's all the same deal of barycentric coordinates. What are but that was great for a segment. What happens if I have a point on a triangle? You have a point P. The triangle has three vertices, A, B, C. What should do, and for each one of them, depending on where P, I want to assign a weight. What will be the weight of C in the denominator? Remember, what did I have in the denominator of a segment? It was the length of a segment. But you expect to see in the denominator now it's triangle. It's the area of the whole triangle ABC. What do I have in the denominator? Look at the three triangles. That's why I went in such a strange way for a segment. You see three triangles that are created by connecting P to the three vertices. You see three triangles. One of them is very relevant for A. Which triangle is the most relevant for A? The one that doesn't have A as a vertex. But for a segment, P between A and B, to determine what is B, what is a W of A, I look at the portion of the segment that doesn't have A on this portion of a segment. For a triangle, look at the triangle that doesn't have a C, as a have another type of way. So here is a triangle that doesn't have A. This is the triangle the area of the triangle BPC, that is the area of this guy, divided by the area of the big triangle ABC, and this is W of A. And similarly, W of C would be the area of what out of the triangles doesn't have C in it, the area of the triangle APB divided by the area of the whole triangle ABC. Cool? And similarly for C. So you sum up always the relationship between one of the sub-triangles versus the area of the whole triangle. And why is this cool? Because now you have these three numbers. Are they in convex combination when P is inside the triangle? Yes, because what do I get when I sum up the area of the three triangles? The area of this plus area of this plus area of this is just the area of the big triangle. So they sum up to 1. They are all positive. What happens when P is outside the triangle? When P is outside the triangle, then they still sum up to 1, but one of the PI will be positive or negative. or sorry, will be either negative or larger than 1. So it's also a check to ask if the point P is inside the triangle or not. That's another usage of it. To know if the point is inside the triangle, I can compute the barycentric coordinates. The same way that for the segment, for W, A, and B, what happens with a point that is on the line, but outside the segment AB, WA plus WB are still 1, but suddenly you have a value that is either smaller than 0 or larger than 1 on the opposite side. Okay, so that's a barycentric coordinate. And again, once you have the weights based on the locations, you can use the same way to interpolate many other properties, any attributes that you'll assign to every vertex. And at this point, I can describe that the main idea behind the fragments programming would be that you have two objects in your calculation. You'll have vertices, and you have a little program that you run per every vertex, and a data structure that is assigned to every vertex that specify attributes of the vertex, like the location of the vertex, the color of the vertex, whatever other attributes, reflectivity, RGB with respect to this shading or that shading, and so on. You can choose which attributes to assign to every vertex. So you'll have one program that runs per every vertex, per every triangle, and you'll have a little other program that runs per every pixel and assumes that the weights are calculated. And now you're saying, given the weights, then a new other property, like the color, is the sum of the properties of the three vertices that define this triangle. So it would be a small program that you're writing per fragment or pixel, and one little program that you run per vertices. And everything else, the compilation and putting all of them together, will happen underneath the hood. It will be sum. Oh, and why are we going through this headache altogether with WebGL? Well, because once you have your WebGL applications, you can run it on different platforms, and it will compile itself and use everything that happens on the machines that you're running it on. It will realize, does it have GPUs, how many processors, and so on, and will adjust it. If it has only a single CPU or single core CPU, just small number of CPUs, it will just emulate running the Z-buffer algorithm per each pixel one at a time. If it actually has GPU, it will squeeze all the efficiencies that you can get from the GPU to get all the parallelization. And once you wrote your program in WebGL, it works just fine without you needing to worry about which platform it runs into. And we'll talk much more about WebGL. Fear no more. We'll give you a whole discussion about WebGL, but WebGL, so historically we have OpenGL written in C that squeezes the maximum power from the graphics, but is compilable per one platform, not transferable between different machines. You have JavaScript that arguably runs on every platform without intervention of you. And WebGL tries to hit both things. It uses not the whole power of OpenGL, but most of the power of OpenGL on one hand, and gives you all the properties of OpenGL, like the buffer algorithm. Okay, so yeah, let's skip this slide, just how more ways to think about the barycentric coordinates. What happens if I have a single machine, a single CPU machine, no parallelization, and let's talk about the restaurant also. So just even computing what is the depth of each point of this triangle. Again, this triangle with respect to different points on this triangle have different z-value. The triangle might be, its normal does not align with the view direction necessarily, so different points, x, y, z, each one has its own depth, and I need to do linear interpolation. And of course, I'll assume that if I do the linear interpolation correctly, then I'll get a planar object, an object that every pixel that I generate should be inside the plane that I define. So you have a point P inside this triangle at the z value of its three values. Now I have the x, y, z of its three coordinates, and I want to compute what is the depth at this point, how far away this point is from the relevant pixel. And you see that I save myself quite a lot of headache by not worry about where is the viewpoint in this point. The viewer is this direction, orthographic projection, not perspective. So I want to compute the depth at this point. How can I do it? Well, what I need to do is to compute the barycentric coordinate, which implies compute the areas of P, this triangle, this triangle, this triangle. What are these triangles? P is one point that I want to compute its depth, one of the many pixels along these triangles, and I need to compute its depth as a function of the depth of A, B, and C. So one way to do it is, it's not the one way. The way to do it is to compute the area of these three triangles. For each one, what did we say the weights that assigned that I give to C? Help, just to see that you're still alive. The weight that I give to C is the area of the triangle that doesn't have C divided by the area of this whole triangle. So sure, and now I need to do it in a raster scale. I have single CPU, I need to check all the pixels over here on this line. And then over all the pixels over here, all the pixels in the next row, the next row, the next row. And per each such row, I need to walk from left to right and compute what is these three areas, WA, WB, WC, for each point across this line. So computing area and division and things is annoying and takes some time, but if P is a unique point, you'll still do it exactly according to the formula. If there is only one point inside this triangle. If you have plenty of points inside this triangle, then you can start saying, you know what, I'll walk a bit more about the gap between one pixel to another, but I'll say some more. So first, I didn't mention it. What happened for P? Here is P. What is in this case? P is on the edge between B to A. What is in this case W of C? W of C is the area of a triangle that you don't see because this triangle is so thin, it's already vanished inside this area. So it's the area of, just as before, the triangle APB divided by the area of ABC, but the area of this guy is 0, so C has zero contribution, and as what happens with these two triangles? That would be T of A, the triangle of A, and that would be T of B. When P moves linearly between A and B, then the same argument, the area is height times base, the base doesn't change, so it's just the height, and the height changes linearly. So it's nothing but when P moves on the edge, what you expect to happen. You're just interpolating between A and C, you're just interpolating between A and B, just on the segment between A and B, and C has absolutely zero contribution. So that's back to the linear interpolation that we had on a single segment. All I try to convince you right now is that the linear interpolation across a segment is just what you think as linear interpolation. That the barycentric coordinates, when it's on a segment introduced, are nothing new. Barycentric coordinates, when all I have is one segment, is just nothing but linear interpolation on the segment itself. So, what the algorithm tells us? Compute the linear interpolation between A and B, and now I have the interpolated values for every point between A and B. In particularly in my image, for every row, for each row, all I have is the interpolated value between A and B across this line. Similarly, do the linear interpolation between A and C. Fair enough? And now I want to compute the depth of each point and for a point P. And I'll remember that for the point P, it belongs to some row. Let's meditate on this row. And across this row, what should happen to the interpolated column to be normal, or exactly what you'd expect. Right? What should be the interpolated value at P? If the formula makes what our intuition said, that you have at this point and at this point some values of Z, of depth, and now as you're moving from this depth to this depth, the depth changes linearly. So just linear interpolation again across this segment. So you can use the formula of linear interpolation across a segment. So the algorithm so far is linear interpolation of 2 points A and B, linear interpolation of 2 points A and C, and now per each row, linear interpolation across this row of the 2 endpoints of this row and the triangle. So that's already much more efficient than computing areas, but wait, there is more. As I'm walking across the line, what happens to my areas, to my linear interpolation? The depth should change linearly across this row. If you think about it, it's triangle, you just cut. You took the triangle, you cut it in some particular height, right here, and the depth across this height, the depth across this height should change linearly. But I'm only asking about the height only at pixels, and the gap between the pixels to the pixels to its right, the pixels to its right, the pixel to its right, is uniform for the whole row. Again, the delta between this point and this one is exactly the same delta from this point to the next one, because these points are equally spaced. So what the algorithm boils out to, compute what is this delta, compute Z right here, and then to compute the value in the next pixel, just perform one addition. One addition, one addition, one addition, until you get to the rightmost point. And move one row below. So it's a constant addition per pixel. Very fast algorithm. Right? So per row, I just needed to compute what is this delta that's relevant for this row. And now I can fill a whole row of pixels. And if I have multiple processors, but not one processor per pixels, at least I can use them to fill each row independently, and in each row, it's just one loop that follows. That is 1 pixel per row, and inside the row, you're running linear algorithm. Cool. And now you have if you ask the Z buffer to compute depth at each point. That's what you'll get, but with the same weight, as we said, you can have approximation, or you can have linear interpolation of colors, or any attribute that you want to have one of them. For guard and fong shading, you'll actually want to smooth corners, and for this, you'll actually have a direction assigned to each vertex, which is surprisingly not exactly the original normal, but related to the original normals. And to get nice effect, you'll have the normal to each point that you'll use for the shading will not be the actual normal to the triangle, because all the pixels have the same normal to the whole triangle. Instead, you'll interpolate normals as you are walking around this point. And you are completely cheating by it because the triangle is flat. But it will look great when we'll get it. Okay, more with the Z-buffer algorithm. So the data structure, we have the area of depth and one array of colors and common in hardware. Yeah, updating new polygons. So as we said, you have one more polygons. Go with it. No problems. Yeah, let's continue. It's a good point. Yeah, we'll wait with homework 2 until I covered a bit more. It's 6:15 and it's good point to cover. What did I cover today? We finished the painter algorithm. I mumbled a bit about construction of BSP. I don't expect you to fully understand it, but you understand that there is an, yeah.
So I was going to say, we're not going to be expected to like have a bunch of lines on the midterm and be able to generate a BSP from that.
No, but what I completely, but the question that I asked a lot of time is, you have a BSP that where no object is crossed by a line. I gave you the BSP. Can you apply the painter algorithm in this case and without any artifact? And the answer is yes. I don't, nobody occludes, or I can camouflage this question as, if I created the BSP and now I create a graph with an edge between every two objects that one occludes the other, will I have cycle in this graph that I create? And the answer is that you will not have a cycle, because the cycle was created when I had the three objects creating this part. Or I can hide it as, here is a quad tree. We'll talk more about quad tree before the midterm. By the way, we need to decide about the time, but quad tree is similar to BSP, but they only cut in the middle. And now here is a quad tree and no triangle or oak tree, because it lives in 3D, and every triangle that they have, no triangles had to be shared between two nodes. Can I use it as a BSP? And the answer is absolutely yes, because it doesn't matter that it's quad tree, it's still nice plane that I created by them. So we talked a lot about BSP without talking much about the construction of the BSP. We talked about barycentric coordinates. That is absolutely essential. Do read more about it. We talked about how to compute the barycentric coordinates quickly using this rasterization algorithm that essentially went one row at a time and handled all the row by just adding a value when you're moving from one pixel to another. And we talked about the Z-buffer algorithm as a whole concept. And I still didn't prove to you that it's only work with orthographic, but it's not a real any limitation, because it's just one fancy matrix that you put at the end and multiply by everything, and it will resolve, and it will wrap or distort the world from being a perspective transformation into being orthographic one. Thank you. Stay here for tomorrow.
Oh, bro, that's nice.
It was really funny.
I'm so bad, bro.
I'm not happy with the scary
I was
questions.
having such a good time, and then like
I
he's
finished
standing
that,
there, and I was
but
like,
Yeah. I can just, yeah, I'll run.
I was like, what are your notes?
So shit, the next 2 days, but right now.
I'm glad you enjoyed that. I didn't realize you saw it too.
Fucking bro.
Jack shit.
I was really proud of you.
Literally that.
I like the arm hair.
Right?
Yeah, that was good.
Oh, I'm sorry, I got it.
I'll meet you up there.
Bye, see you.
Yeah, bro.
Oh, my butt hurts.
Oh my gosh,
Ooh,
bro.
off the backboard is really good.
I should, yeah. I should have did that. You're way cooler than me, bro. You just, is that why he's asking?
No. Imagine, no, there's a baby mantis that he knows.
That is insanely good. That's so funny.
Yeah. Thank you so much. I thought you guys would find it entertaining. It's pretty funny, right? I like the little.
Elon, you
No
see this?
way!
No, you should show him. That's the coolest thing ever.
Pretty cool.
Look at this.
Oh, wait, he's so cute.
Oh wow, he's so small.
He's so cute.
Look at this one.
It's cute.
I thought that was pretty good. That's pretty
That's
good job.
fantastic. Please send it.
I will.
This is great.
It has your little monster and everything. I'm glad you like it.
I do.
That's awesome. They're so tiny.
I know they're so
Yeah,
little.
yeah,
you so much.
You have a bit of a pepper for the fly to survive
Yeah,
more than a
thank
few
you.
hours. There is a bit moth, so you can.
so much.
That's so cool.
So
He's so
that's for you.
cute.
You're familiar with moth, right? That
Yeah.
It just saves the humidity and some fruit flies.
Yeah, I
I
got a
fed him
little
today, so
pink
he
for
should
him.
be good.
Thank
For
you
another
so
food.
much.
Do you
I
have a
love
way
him.
to take this box, or do you need a more rigid box?
I'll be okay with this. I have a jar for him in my car because I was expecting him.
Okay.
Yeah, I have a
'Cause
little jar for him.
Yeah, I put this box in this one just to not
Keeps
get
you
it smashed.
safe. Yeah.
Sure.
Yeah, I'll
But
put him right
mhm.
in my little jar. I have a jar for him.
Okay.
Thank
Very
you
good.
so much. I love
Mhm.
him. Look how cute.
Yeah.
Not expected to this small.
He's so adorable.
Yeah,
Thank
the-
you.
The body language of these animals is. Questions?
Yeah, I had a question about assignment to homework tips.
Sure.
So I wanted to know, like, how would the assignment be graded exactly? Like, you have the metric, but do the Jeff or the rendering have to match exactly what you expect?
No. There is no automatic part. I'll let you know if I have some eggs now that I'm waiting for
Yeah.
hatch. From these ones, I didn't. I only had 2 left, so you got one of the 2.
Thank you so much.
Okay.
I love him.
And again, no problems to if you need to.
No, he's going
Okay.
right. I got a little jar for him, and it has little moss and everything, so he should
And
be a happy
you
boy.
and you have flies, so you have
Yeah,
to.
he's prepared. He's prepared. Thank you so
Perfect.
much. Have a
Sure.
great one. Thank
Thanks.
you, Professor.
Yeah, there is no automatic grading. We look for artifacts. If it looks, then we feed a different JSON. Then we look at if it didn't crash so far, we look at the code and see that it makes sense and that there is no end to the 4th loop. Like I had people that solved it by for every pixel, ask every other pixel, every other object, something like that runs in the number of pairs or triples of pixel in all the images, that there is no need, that is it. The part that maybe I hope that people solve more or less themselves, but at least is that constructing that when you have a billboard, an image of a person, here that you can take a ray, find where the ray hit, and ask, am I in a red point or a white point? And copy the color accordingly, and that's a good part. That I thought the hardest part of the homework, so I might look at how your algorithm does it and to see that you're using the alpha, beta, or whichever other mapping you want, but that once you realize that a point P hits the plane that contains a billboard, then from knowing P, you can ask, is this inside the billboard itself, and the coordinates that basically using the billboard as texture, you have to solve the texture mapping.
But basically like the calculating the distance and dividing it by the billboard width and everything.
Yes, but
Yeah.
the billboard, of course, might look like billboard might. There is no reason to assume that its bottom is horizontal, or that it could be that the billboard face to the opposite direction, and then you need some default here. I don't care. And of course, it could be that the way that the billboard looks at the image plane, and why it so the lower left is much closer to you than the upper left, so it should appear as a trapezoid, but not.
But
Yeah.
and another thing is like while I was working on this rendering the spheres and the diffusion and shading on this. So the question I was like, what should be the intensity of the light? Because right now it's I put it at maximum, so it's appearing white over here. But if I reduce the intensity, obviously the color would change a little.
Well,
So
even if the light is maximum intensity, but when you hit a surface, you start by multiplying it by by the ambient coefficient of the surface.
Right.
So if the sphere is blue, and at this homework I don't ask for a specular reflection, only for diffuse. So, I mean, if you have specular, then you don't need to remove it. But for diffuse, if it was blue, it should stay blue. Remember the difference between diffuse and specular?
Okay.
Diffuse I only multiply by the cosine. Specular, it's a strange way at which specular, I don't care actually what's the original color of the object. I just ask color of the light versus perfect reflection. So without diffuse, it shouldn't be white.
Okay, because what I'm doing right now is if like I'm calculating the diffuse factor, and if it is less than or if it is less than 0, I'm just putting it as maximum. So that's what I'm doing right now.
So I have one light L Z R G B equals 111, and this light hits the sphere, and I look at this direction versus a normal.
Okay.
So it's a cosine of this, so it's n times L times what this will be smaller than 1 always. If it's negative, I ignore it completely because it means that I'm somewhere here. But if it's positive, I say it's this times the color that I would have returned it if at the maximum one. So the coefficient, if it's blue, and I don't remember from the file, but if it's blue, then it should be, for example, 0.9, 0.1, and 0. So that's the ambient color. So I take this times cosine. So in diffuse only, if I have nothing that returns red here, then it should not become white.
Okay, I think I'll look into
So,
this.
okay. And do you have an example with, so, yeah, I don't know how, I mean, these look like specular spots, so maybe you did add specular there, and specular does have a whitish spot. Spe-
Check. Yes, right now I'm calculating. Okay, so I'm calculating the normal where the light is hitting, and also getting the direction of the light and doing the dot product.
Yeah.
Just try doing this instead.
That's crazy though, huh? I mean, it's not Google search, right? Yeah, clearly. So like, and then Tia said, see that there's certain things or procedures change, right?
And I'll try to debug it a little.
Like the ChatGPT talked about heat push,
Uh,
heat pop, right? For a heat, you don't usually talk about
Now,
talk about
the similar homework last year, we did ask for to have specular. So, for yeah. But anyhow, in this case, you're just taking the color of the object as if the light points directly on it, which would show it completely blue for this sphere and completely green for this sphere. And you dim it by cosine, dim it because it's between 0 and 1, but you never add more lights from other sources. Specular says I don't care what the object, I don't care if it sums up to 1 or more than 1. If you are like in the direction that the light points directly at you, it's perfect mirror. You're getting all the direction of the light independent of what's the color of the surface.
I'll try to debug this a little bit more.
Sure, and we can speak Zoom, etc. And the billboard looks okay.
Yeah, like I just started with this. Like I had done the homework